Imagine a tiny, almost invisible flaw in something crucial, maybe a small crack in a bridge support or, a microscopic defect in an aircraft wing. How does that seemingly tiny starting point lead to a catastrophic failure? And why do some materials like glass seem to just shatter instantly, while others, like certain plastics or metals, they bend and deform quite a bit before ever giving way?
That's a fundamental question, really.
Today, we're doing a deep dive into exactly that, exploring the fascinating and, frankly, critical world of fracture mechanics. Specifically, we'll focus on how brittle materials, the ones prone to sudden breaks, fail when they have stress points, and how scientists are getting, well, remarkably better at predicting these hidden pathways to failure.
It's a really active area of research.
Yeah, and our source material for this deep dive comes from some cutting-edge research by E.V. Feklistova, A.I. Mugatarov, and V.E. Wildeman, published just this year, 2025, in Fracture and Structural Integrity. This paper offers a fresh perspective on numerically modeling these fracture processes, taking into account some surprisingly complex but essential factors that previous models often kind of missed.
Right, they're adding layers of realism.
Exactly. So our mission today is to unpack the most important insights from this research. You'll discover why understanding the statistical nature of material strength is so crucial, and how even a small design feature can fundamentally alter how things break, and a groundbreaking new approach to modeling the partial loss of a material's ability to carry a load. Think of it as a shortcut to being really well informed on this tricky topic. And understanding these details, it's not just for engineers, right? It helps you appreciate the hidden complexities in the materials making up our whole world, from, car parts to your phone screen. You'll probably gain some real perspective on why things sometimes fail in ways that seem really unexpected. So let's dig into this, because fracture isn't just an instant snap, is it? This paper describes it as a complex, multi-stage process, starting really small at the micro level and growing into something much bigger.
That's absolutely right. You can think of it almost like a chain reaction. It often begins with these tiny inherent imperfections or microfractures. These then sort of evolve into microdefects. Then these individual defects start linking up, forming larger damaged zones. And eventually they consolidate into what we call macrodefects, and ultimately the main cracks we can actually see.
Okay, so it's a progression. And to understand and predict this complex journey, engineers rely on mathematical models. The paper mentions several approaches, but it highlights one that's deceptively simple, but still widely used. Basically, reducing the stiffness of local areas when some failure criterion is met. But what's really intriguing here is that it's not just about one weak spot failing in isolation. It's about how that failure redistributes stress, potentially causing neighboring areas to break too, like a domino effect.
Exactly like a domino effect. That stress redistribution is absolutely key. And to manage this complexity, engineers use various models of what's called damage accumulation. For instance, some models might track how different parts of a composite material degrade, like the reinforcing fibers, compared to the surrounding matrix material. Others might use concepts like strain energy to predict the overall damage after a sudden event, maybe an earthquake or an impact. It really raises a crucial question. How do you accurately capture that full progressive journey of damage, not just the final breakpoint?
Right. And here's where it gets really interesting, I think. You might intuitively assume a material has one single fixed strength value. But this deep dive reveals that a material's physical and mechanical properties, especially its strength, aren't fixed at all. They're actually random values.
That's a critical point.
They vary, even within the same piece of material, across a certain statistical range.
And if you think about the bigger picture, considering this inherent statistical spread of properties isn't just, an academic detail. It's absolutely vital for accurately predicting a structure's real-world reliability, its ability to survive unexpected loads, its overall capacity to bear weight. And what's even more crucial, actually, is that the specific type of statistical distribution you use to describe this variability, not just the fact that it varies, that significantly impacts the accuracy of the model's results.
Okay, so the randomness matters, and how you model that randomness matters too.
Precisely.
And then we add another critical factor into the mix, one that can totally change how a material reacts. Stress concentrators. Think about drilling a hole in a metal plate, or maybe a sharp corner in a plastic part. The paper really emphasizes that the mere presence of something like that can dramatically alter the strength of the entire structure.
Absolutely. There's a huge amount of research dedicated just to this phenomenon. For example, some studies on circular holes found that the stress concentration coefficient which
Yeah.
is basically how much the stress gets amplified right around that hole, could drop from a factor of 3 under a simple pull.
Okay.
Uniaxial tension down to maybe 2.1 when you're pulling from two directions, biaxial loading.
Ah, so the loading direction matters too.
It does. And what's really insightful here is that statistical strength methods, the ones accounting for that random variation we just talked about, have even been shown to better predict how cracks actually propagate around these concentrators compared to other, simpler approaches. This all just highlights the significant impact that multi-axis loading forces coming from multiple directions at once has on structural failure, especially when these concentrators are present.
Okay, so if those older models had these blind spots, maybe predicting materials were weaker than they are, or oversimplifying the breaking process, how did Feklistova and her colleagues tackle these issues? This seems to be the core of their work. What specific assumptions did previous models make that just didn't really reflect how real brittle materials behave?
Well, a couple of key things. Previously, models often used, let's say, simpler statistical distributions that could sometimes generate unrealistically low strength values, basically predicting weak spots that weren't really there. But perhaps more importantly, they frequently assumed that when a small simulated piece of the material, a finite element, failed, all of its stiffness properties were just gone, completely lost.
Right, like it just vanished.
Exactly. And that just doesn't quite match how real elastic brittle materials behave. They can definitely lose their load-bearing capacity across a crack plane, but they can often still maintain strength along that same crack plane. Think about wood grain strong along the grain, much weaker across it. That directional difference in strength is called anisotropy.
Ah, okay.
And it's a critical factor that this new model now captures, which makes the predictions much, much more accurate.
So this is where the real innovation comes in. How exactly did they improve the methodology to capture this more realistic behavior?
The key innovation is how they model this partial loss of bearing capacity. So when the material's first principal stress, basically the highest stress acting on it in any single direction, reaches its ultimate strength, the material, which might have started as isotropic, same properties everywhere, transforms into an orthotropic one.
Meaning its strength now depends on the direction, like the wood example.
Precisely. Its strength now varies depending on the direction of the applied force. And crucially, the axes of this induced anisotropy are aligned with the principal stresses at the very moment the damage happens. This effectively means the model simulates a crack propagating through the material where resistance is lost across the simulated crack plane, but importantly, it's maintained along it.
I see. So if that partially damaged material then experiences stress again, but along the direction where it still has some resistance, then it completely loses its bearing capacity.
That's the idea, yes.
That sounds much more physically plausible, more nuanced.
It is. And it also introduces what's called geometric nonlinearity into the simulation because once a material is completely fractured, it becomes extremely malleable, essentially very floppy. For their specific setup, they focused on an elastic brittle material, one that doesn't permanently bend before breaking, no plastic deformation. And they used a 3-parameter Weibull distribution for the ultimate strength. This specific statistical model is much better suited for describing real material properties because, unlike simpler 2-parameter models, it avoids predicting those unrealistically low strength values near zero.
Got it. And they applied this sophisticated model to a specific test case, right?
Yes, a very specific scenario. A 100-millimeter square plate, just 1 millimeter thick, with a 20-millimeter circular hole right in the middle. And they subject it to forces applied from 2 directions simultaneously. That's biaxial kinematic loading. They ran many detailed simulations using professional engineering software, ANSYS, which even has features to model crack growth by effectively killing or removing finite elements as they fail, simulating how the damage progresses.
Okay, so very detailed work. What did these simulations actually reveal about how materials truly behave under these conditions, especially compared to the older models?
The comparison was quite striking, actually. The new model, the one considering partial bearing capacity loss and the resulting anisotropy, led to a significant distortion of the loading diagrams. Those are the graphs showing how the material responds to force over time.
Right.
It also showed a noticeably longer post-critical deformation stage, meaning instead of the material just snapping abruptly once it reached peak load, the new model showed it would actually continue to deform, sometimes quite significantly, after the peak load before total failure. This gives a much better picture of, say, how much warning you might get.
That sounds incredibly important for safety.
Absolutely. The previous, simpler model which just reduced all stiffness at once, often ran into problems where the numerical solution became unstable. The simulation basically crashed. Furthermore, with the new model, a sharp drop in the load carrying capacity along one axis didn't always lead to an immediate abrupt drop along the second axis. Why? Because resistance was being maintained in that transverse direction due to the anisotropy. This really demonstrates the greater predictive capability of the new approach, especially when you have complex multiaxial loading scenarios.
That's a huge step forward in understanding, definitely. You also mentioned they looked at how the coefficient of variation, or CV, of the strength properties affected things. That's the measure of how much the strength varies within the material itself, right?
Yes, exactly. How spread out the strength values are.
What do they find there?
They found that increasing the CV, meaning more variability in strength, consistently led to a more gradual decrease in the material's overall bearing capacity. It also reduced the amount of displacement or bending the material could handle before reaching its maximum load. This observation also revealed a nonlinear deformation curve with that distinct post-critical stage, again reinforcing that gradual rather than sudden failure mode when variability is high.
Interesting.
However, because they use that three-parameter Weibull distribution, which inherently avoids extremely low strength values, there weren't elements predicted to be super weak. This meant the loading diagrams remained practically linear right up until the maximum load was reached. This contrasts with previous models using different statistics, which often showed a sort of pseudoplastic behavior, making it look like the material was yielding or bending plastically before failure, even when it wasn't.
Okay, so the choice of statistical distribution really cleaned up the pre-failure behavior prediction, too.
It did, made it more physically accurate for brittle materials.
And the research also confirmed different types of damage accumulation, how the damage actually spreads through the material.
Absolutely. They confirmed the existence of two main types, which they termed localized and mixed damage accumulation. For lower CV values, say up to about zero point 0.2, the damage was largely localized, meaning it really concentrated right near the stress concentrator, the hole, in their case. A main crack, a macrodefect, would grow pretty much directly from it.
Okay, makes sense.
But as the CV increased, maybe zero point 0.3 and higher, a mixed type of damage accumulation became more characteristic. Here, the macro defects grew, but they grew through regions where damage was more widely dispersed, not just tightly packed around the initial stress point.
So the damage was more spread out before the main crack formed.
Exactly. Now, it's important to note they didn't observe a pure dispersed type of damage, where tiny failures pop up everywhere randomly without a clear link to the concentrator, even at very high CV values. And again, they attributed this absence to the specific benefits of the three-parameter Weibull distribution, which avoids generating those elements with unrealistically low strength scattered throughout the material model.
Fascinating. And they even found a way to figure out which type of damage accumulation was happening early on in the process. That sounds incredibly useful for prediction.
Yes, exactly. They found they could get an early indication by analyzing a couple of parameters calculated during the simulation. One was the average distance from the hole to the elements experiencing the highest stress, which they called lambda. The other was simply the number of these highly stressed elements, which they called eta.
Okay, lambda and eta.
Right. And what's really neat here is that the diagrams of these parameters, when you plot them against that coefficient of variation, CV, show distinct behaviors. For instance, when the lambda value, average distance, and the eta value, number of elements, initially decrease as CV goes up, but then kind of level off to horizontal sections,
Yeah.
that leveling off serves as a clear indicator of the transition point where the failure mode shifts from being purely localized around the hole to that more mixed type involving dispersed damage. So it provides a really valuable diagnostic tool derived right from the simulation data for understanding and predicting how a specific material with its inherent variability is likely to behave under stress.
Wow, okay.
Yeah.
So we've really taken a deep dive into this complex world of fracture mechanics today.
Yeah.
We focused on how brittle materials, especially those with internal flaws or stress points, break under load. We've seen how absolutely crucial it is to consider the statistical variation in material strength. It's not just one number. And how things like holes or sharp corners, the stress concentrators, fundamentally change a structure's behavior. And most importantly, I think we've unpacked this groundbreaking modeling approach from Feklistova, Mugatrov, and Wildeman that considers the partial loss of load-bearing capacity and the emergence of direction-dependent strength, anisotropy, during fracture. This provides far more realistic and predictive results than what was often possible before.
Absolutely. This improved numerical model, especially with its more refined statistical approach using that three-parameter Weibull distribution and the detailed simulation of partial damage and anisotropy, it really does offer significantly greater predictive capability. And like you said earlier, this isn't just an academic exercise. It's a vital tool for engineers assessing and designing reliable structures made from all sorts of brittle or quasi-brittle materials, things like advanced ceramics, many polymer composites, even concrete to some extent. It ultimately helps engineers build safer, more durable products across countless industries.
So maybe a final thought for everyone listening. Next time you pick up your phone, notice the glass screen, or maybe you walk past a large concrete building, or think about components in a plane or car. Consider this hidden world of microscopic material weaknesses and how they might fail under complex, real-world stresses. How might this deeper understanding we've talked about today reshape the way we design everything for better safety, longer durability, and maybe even greater efficiency in the future? Something to think about.